Hello everybody to this video presentation. In this video we present preliminary work on a universal robot platform we designed and built for disaster response. This is joint work between the Graz University of Technology and the company Inetic, and we want to acknowledge the support of the Austrian Research Promotion Agency and the Disaster Competence Network Austria. So we all know that ground robots were more or less successfully deployed in various disaster response scenarios, but the deployment scenarios are quite heterogeneous. For example, on the right-hand side, you see use cases we are looking into. So we have the exploration or reconnaissance of remote areas. Here it is desert-like. We have reconnaissance and transport in alpine regions like in the middle, but we also have use cases, for example, in man-made infrastructure here, like in a tunnel for cars. And as the use cases are different, of course, the robot platforms are itself and their capabilities are quite different. In particular, we have to distinguish the locomotion systems. So usually you have wheels or tracks or legs, depending on the use case. Sometimes they are combined. Another important factor is the size and the payload. And according to a paper by Robin Murphy, we have this basically three categories. We have man-packable, which is a small one you can put in your backpack. We have man-portable, which is at least two people can lift up, and we have maxi systems. And of course, depending on the use case, we have other parameters like the endurance, how long it should work, what is the speed of it, what is the precision of the movements the platform can do. And what we see is there's not really a good overall system on the market we can use for all our use cases. So that's why we want to provide in this or we want to work on a capable universal platform for this kind of use cases, basically disaster response and field robotics. When we look into the design goals for the key performance indicators, what we are looking in particular on is we want to manage challenging off-road terrain. So we are not only for urban disaster response, so we want to go to the outdoor world, as we have seen before. For example, if you go to alpine regions or if you go into remote areas. Another point is most of the robots we see in disaster response are more or less used kit steering, and we want to have a little bit more precise navigation, because if you want to do manipulation or extraction of samples, it would be nice if you have a more precision in the navigation. It's also good to have one system which might be able to manage variable speeds from low speed in precision navigation to larger speed when you traverse from one location to another one. And the payload, it should be, on one hand, it should be high so that you can put on various instruments, and you can also use it as a transport vehicle. And it should also be flexible so that you can easily exchange it for different purposes. Here we looked, and that's our personal view here, into what is on the market. And in no way this is a complete list of all the good platforms that are available, but that's the usual suspects. And we have here, for example, the ClearPass Warthog, which is a well-established um, platform for research, but it is limited in its top speed, and it is also limited in how to manage rough terrain. It is based on a swing system in the wheels. It is able to do something, but it's not perfect. Of course, then we have the other ones, which more coming from the EOD domain, which usually use tracks like the Deodor. They work fine, but of course they are optimized for, or they are well loved by the researchers based on their robustness and performance. But of course, navigation is still skid steering, and you not can go on higher speeds, and it's also not very much optimized for off-road terrain. And there's the same for the Andros system from Norseman Grumman, which is have a nice combination of wheels and tracks, but still has a limited speed in the navigation. Okay, so that's the reason why we came up with our own design for a platform, and you see here the first completed version on the right hand side. What was the parameter we're looking into? So first of all, we wanted to have that it is drivable on very low speed, smaller than 1 meter per second, and should be able to be more nicely navigatable than a skid drive. But it should also go on a higher speed. We tried it, or we want to do it until 40 kilometers per hour in order to increase the radius of operation, so you don't have to carry it somewhere. It can change its operation mode and move on to another place. Precision locomotion I already mentioned, and it should be able to do off-road terrain, challenging like here. It's not very much off-road. It's basically yeah, an unpaved road in the Alps, but this should be manageable without any problems. And the payload here, it's basically a plate which can be removed, and in this case it is a payload for vision-based navigation, and you can simply remove the entire plate from the platform, and there's only one power and Ethernet connector and a few screws, and then you can remove it. And what our idea was at the end, that we combine our knowledge in field robotics with our expertise in automotive engineering, where we have worked with basically electric autonomous cars, and we wanted to combine these two worlds and combine the best of both worlds. Yeah, this leads to the mechanical architecture. Um, the basis is a commercial electric vehicle. It's called Jetfly. It is a moderate-sized quad, which is also used by, for example, the Austrian Postal Service, and has all the advantages of automotive engineering. So you see, we have a suspension, which means that we can go over rough terrain. You see details on the right hand side. You see the steering, you see the brakes, the suspension, and you see also on the lower side, on the lower image, the actuation for the automatization of the vehicle. And of course, I mean, there's a reason why cars are built as they are built, because they are stable. They are also drivable nicely on higher speed. They can also go off-road, so that's quite a good combination. What is a little bit an adaptation, it gives also trick, or is also tricky for the control, is that we have 4 wheel hub motors, quite powerful. They are individually controlled, and we can individually control each of the four wheels. So that means we can go beyond Ackermann, even if we go off-road, and can move, make, for example, to some extent, grab moving, grab-like steering, for example. And we already have a payload of 300 kilo, which is possible, and theoretically with the actuators we can go for 60 kilometers per hour. We have not tested it yet, I have to confess. Yeah, the electrical architecture um, is basically focused on the power and the safety we need, because um, the vehicle by itself already has 350 kilos plus the payload and the velocity, so it's basically a safety critical instrument already. What we have done, and you see the overview on the right hand side, is basically a full drive-by-wire system. So the wheels and the actuator, the steering is fully electronically controllable. We have a real-time electronic control unit there where all the control runs on real time, which is in particular important later on when we go with higher speed and have more dynamics. We have a standard 48 volts lithium iron battery pack, which is usually good enough for 2 to 4 hours of operation, even if we go quicker with the platform. And what is also important is we have a quite good elaborated safety concept, because the problem is if you run out of batteries or you crash somewhere, then it's hard to recover with this platform. That's why, for example, we have a brownout monitoring in there, which brings the system in a safe state even if the battery goes down. But before it is completely out, that we get the safe state. We have quite a good emergency stop concept with a lot of emergency brakes around or emergency stops around the vehicle, including also monitoring and also a remote e-stop in case for safety. From the software side, we use two layers. As previously mentioned, we have a real-time controller on the vehicle, which takes care about all the real-time aspects. So controlling the actuators, looking for valid motion patterns, and supervision of the relevant aspects like power consumption and actuator status. And we provide basically emission-specific hardware, software, which runs on the payload, which can be connected via Ethernet cable to the platform, and there you can do what you want. We support ROS, so the mission-specific software can be run on ROS and can immediately work with the platform. In order to take into consideration the two operation modes, we have one is a standard twist message interface, which can be activated up to 1 meter per second, which allows precise locomotion, and it is also, of course, beyond the capabilities of a regular Ackermann or differential drive. For safety aspects, if we go at a higher speed, then twist matches are not allowed anymore. Then we use motion primitives, and these motion primitives are commanded to the machine and executed there on the real-time controller. We have also, and you see it on the right-hand side, a Gazebo simulation. So we started already the development of the mission software in advance of the platform was there, and allows to test navigation software. And The software running on the vehicle was modeled and verified with the UPAL tool set, which is basically a modeling and model checking tool, so that we don't have any safety critical issues in the platform or in the platform controller. So this brings us to the preliminary results and the conclusion. You can see on the right hand side the videos of preliminary test runs we did in an Alpine region. What we did so far, we built up the entire platform, so it's there. We're able to drive it. We have tested it with limited speed so far. It's about 2 meters per second on paved roads and moderate off-road scenarios like you see here. What you see is the concept is suitable. It works. It can even with a high payload, it can, or a high weight, it can go off-road and have a precise or allows precise navigation. What we also found out already in this preliminary test is the steering actuators needs to be more powerful. In particular, we have more load on the steering actuators when we go off-road than in the classical on-street scenario. And of course, the dynamics in the control must be more accurately considered. In particular, what we saw is the driving on different environment conditions, like up the hill, down the hill, in off-road scenarios through a ditch. It's not yet optimal, so there needs to be new or improved control strategies to be integrated into the platform. So this brings us to the end of the presentation. Thank you very much for your attention. I hope you enjoyed our preliminary results on our universal robot platform disaster response, and we are looking forward to discussions around the virtual conference or on any other channel you might reach out for us. Thank you very much, and goodbye.